Hi everyone, welcome back to my Z80 computer series. So, testing the keyboard. Finally got the full keyboard made. I've made the modifications to the trainer board to add another socket here to allow me to connect the keyboard to it. So I'm actually super excited to get this keyboard up and running, test it, see if it works. But before we do that, I'm going to give you a little bit of an explanation on what was required for the schematic diagrams to actually get the keyboard circuitry added to the trainer board. I'm going to have a very brief look at the Z80 assembly code, some small tweaks that I had to make to adapt it for the full keyboard, and then we will get into powering this thing up. Well, I'll start with the schematic of the keyboard switches, matrix that we've got here. And there are two main differences from the previous one, the keypad that we did previously. The first one being quite obvious is the sheer number of switches. So we now have a full 8 columns and 8 rows, which gives us a potential of 64 switches. I've only actually got 63 connected. There's a space down here in the corner. And the second main difference is the orientation of the diode is now pointing towards the switch. So the electrical current will flow in through the columns, through the diode, through the switch, and then down through the rows, which is the opposite way to how it worked on the keypad. Then we just got our connector here. It's a 16-way connector this time because we've got 8 rows and 8 columns. That's about it for the keyboard matrix, straightforward. So then we've got the actual trainer board itself. I'm on sheet 3 here. These schematics will be made available in the GitHub repo, so if you want to study them at your own pace, you can download them from there. The main addition here is this new buffer, and essentially this circuit here around this area. So we've got the new buffer connected to the data bus as usual, as per the other two that are already there. And then the inputs of the buffer are connected to our keyboard connector. I've numbered these C20 through to C27. Incidentally, I've renumbered the keypad ones C10 through to C15. My thinking here is that I needed to use different numbers because these are not connected together. So I just elected to prefix these ones with a 1 because they're port 1, and these ones are starting with a 2 because they're port 2. Really doesn't matter what numbers you use, just has to identify with these net flags over here on the keyboard connector. I've elected this time to use pull-up resistors. I believe that's a more conventional way of doing it. It's the opposite to what I did on the keypad where I used pull-downs, as you can see here. I only really did that to compensate for a mistake I made on the keypad. I had the diodes around the wrong way. And I didn't feel all that comfortable fitting the diodes opposite to what the actual PCB printing indicated. So I decided to just swap it around in the software and go with pull-down resistors. But we're of course going to have to swap that back in the software now because we're going to be using pull-up resistors. I really wish I hadn't done that, but I did. So then the only last connection that we need to make is the enable line here. We've got import 2, which enables this buffer chip here. So it's really quite simple. That's all there is really. There's the buffer connected to the data bus. The other side of it connects to the keyboard matrix, and we have the pull-up resistors, and there's just this one enable line here on our input decoder chip. So that's the schematic. Let's have a look at the assembly code. So I've got the assembly code here. It's very similar to what we did before with the keypad, so I'm not going to explain this all line by line. But all the code will be made available on the GitHub repo. Again, I'll put links in the description. So if you want to download this code and you want to study this code in your own time, you can do. I'll just talk you through the changes that I had to make it work with the full keyboard. So the main loop and output A are both the same as before, so I won't cover those. Then we've got the keyboard read routine. There's a change here. The D register is loaded with the number 8. This is the number of ports or rows to check. We've got 8 rows this time. I think we had 3 rows last time. So we've changed that to the number 8. And here, this is actually the port number that we put into register C. Before it was number 1 for the keypad. This time it's number 2 for the keyboard. So that's port 2, as we saw on our schematic diagram. The next change, I believe, is here. Now this is the number of keys in the row. So before I think we had 6 keys in the row. Now we've got 8 keys in the row. So that's the number 8 there. And then this is an important change here. We're now jumping when we're not carrying, whereas before we were jumping when we were carrying. So previously it was JRC. It's now JRNC. If the carry flag is not set, we found our key. So we're shifting the bits to the right and they're dropping out into the carry flag. And if a 0 drops into the carry flag, we've actually found a key. That's a key pressed. Whereas previously, if there was a 1 drop into the carry flag, we'd found the key. So that's the inverted logic between the pull-ups and the pull-down resistors. And then other than that, this all remains the same. So other than that, it's just the actual keyboard map here. We've now got 8 rows. And in each row, we've got 8 values for the 8 keys. Most of these are the ASCII codes. So I've just used the strings and the assembler will convert them into their ASCII codes. But some of the keys don't have ASCII codes, like the cursor keys. Left, right, up, down, etc. They don't actually have ASCII codes. So I've just arbitrarily assigned some of the lower numbers to those. But some of these are valid ASCII codes. I think we've got the escape key is code 27. The tab, I believe, is... can't actually remember if tab is 8 or 9, but it's one or the other. Then we've got the enter key is 13. But some of these codes are just arbitrarily made up. I just randomly assigned ones that were kind of spare. Doesn't really matter. We just have to document what we did, really. Just briefly mention these numbers here. These are the addresses that we load into register B. The code is somewhere up here. Here, load B, HL. So that's these numbers here. They might look a bit strange, but if you convert them into binary, you'll understand what's happening. These are the 8 top bits of the address bus, so the top half of the address bus. And if you write this out in binary, you'll see the very last bit is 0, and then as you move down, bit 1 is a 0, and this one's got bit 2 as a 0. This one's got bit 3 as a 0, bit 4 as a 0, bit 5, bit 6, and bit 7. All the other bits are set to 1. It'll make a lot more sense if you write that out in binary. I won't do that for you. I'll leave that for an exercise for you to do yourself. But if you're wondering where those numbers come from, we're just driving each address line low, one at a time, as we scan through the keyboard. So that's the changes to the software. Let's get over to the exciting bit and get this keyboard plugged in and see if it actually works. So, moment of truth, will it work? I'll power up. Hopefully we won't see any magic smoke coming out, as they say. Yeah, age-old problem here of the power on reset. I have got my fast clock running, which I thought would probably solve the reset issue, but clearly it doesn't. So if I hold down the reset key and let it go, the green LEDs over here, I'll try and point over here, went to 0, which is a good sign. We got the top half of the address bus flashing away. That's another good sign. Probably indicates our program's running. Trying to show you on the screen here, I've actually got my input voltage set to 8 volts. And we can see that we're drawing a current of about 0.8 amps. I've got a current limit on this of 1 amp, so I'm sitting just below that at the moment. In theory, it's a 2 amp regulator over here, but I can't really vouch for the heatsink on that. I don't really know. I haven't done any calculations on that. So let's press a key. Let's see what happens. So if we press the escape key, we should see ASCII code 27, but of course it's going to be hexadecimal over here. So I believe that would be 1B. So if I press escape, we do get 1B. So a bit of an anticlimax, but that's really all we're going to get out of the test. I'm going to go through every key and just check the codes. I've got them written down here. So number keys should be 31, 32, 33, 34, 35, 36, 37, 38, 39, and then 30. Got to keep looking at my chart. So the next one should be 2D, which it is, and then 3D. Yep. 08. Was that that key? No, that was 3D, so this must be 08. The next one is 09, that's the tab key. Then 71 for Q. Yep. Then 77, 65. Losing track of which keys I'm pressing. 72, 74. 79, 75, 69, 6F. Next row is 70. Yep. 5B, 5D. Enter key should be ASCII code 13, but that's 0D in hex. 0D, and then we've got 0B, 61, 73, 64, and the next row is 66, 67, 68, 6A. Is that 6A? Yep. 6B, 6C, 3B, 27, next row, 23, and we're down here, 0E, yep, 7A, 7-8, 6-3, 7-6, 6-2, yep, and 6E, new row, 6D, 6C, 2E, sorry, I think I said 6C, it's not 6C, it's 2C, that is correct, 2E, 2F, 5C, 0E, 0F, yep, and 1-1, 1-2. Space bar would be ASCII code 32 in hex, that would be 20. Yep, 20. 1-3, 1-4, 1-5, 1-6, and 0F. So they all work. I just want to remind myself something here. We've got a control key on either side of the keyboard, and I think I assigned them the same code. So this should be 0F, and this one is 0F. I think we see the same on the shift keys. This is 0E, and that's 0E. I think everything else should have a unique code. So it's working quite nicely. I mean, it's a bit of an anticlimax because we can't really give any good demonstration because I don't have a display yet, but it does prove that it works. And it worked first time, first try. Would you believe that? Well, no, it didn't. I'll come clean with you. I could have done this video a little bit differently. I could have shown you the problems that I faced and shown how I went about diagnosing those issues. And whilst I think that actually would have made a really interesting video, I just wanted to be certain that I could actually get this thing to work before I put the video out, before I started to record. Kind of wish I'd recorded it because it didn't turn out to be too difficult. I'll briefly explain to you what happened. Initially, when we first turn on, if I show you that again, if I power off and power on, usually it gets stuck because the reset doesn't work properly. But we reset and you'll see over here it goes to 0, 0, which is correct. That's what should be happening. But what was happening, it was actually going to 1B over here, which I misread and thought that it said 1.6. And it took me absolutely ages to figure out why it was doing that. And eventually it turned out to be a faulty chip. The buffer chip I'd put in was faulty. You could see by looking at it, it was a second-hand chip. It was a bit corroded, the pins were bent. It looked like it had a hard life. So it's probably damaged. So I swapped it out for this one, which was clearly a brand new chip, because you could tell, because when you first use these DIP ICs, these dual inline ICs, you have to kind of roll them. You have to roll the pins to get the pins straight to go down into the socket, and I had to do that. So it really did look like a brand new chip. Plugged that in, and then we started to get some kind of sensible behavior on here. When we pressed the keys, we actually saw responses, but they were the wrong responses. They were the wrong codes. It didn't take me too long to realize that they were exactly backwards. It was if I was running through the keys backwards like this, as I just did, but going backwards. It was the exact right characters, but just completely reversed. So I figured that must mean that I've got both the data bus in reverse and the address bus in reverse, which really points us to this connector, doesn't it? I'd misinterpreted where pin 1 was. I did look at it, and then I flipped the board over, did the wiring, and got pin 1 at the wrong end. I did try and correct for that by cutting the connector off, turning the connector around and reconnecting it back on, but I couldn't get it in the correct orientation, so in the end I had to unsolder all the wires from underneath and resolder them into the correct positions. It still didn't quite work. All of them worked, apart from it seemed like rows 1 and row 2 seemed to be tied together. Didn't matter if you were pressing keys from row 1, keys from row 2. I think row 2 starts, we've got 8 keys in a row, so this is 1, 2, 3, 4, 5, 6, 7, 8. So the second row starts here, and then they started to repeat the codes from the first row. But that was, again, fairly obvious. It's like 2 address lines are tied together. Incidentally, it didn't seem to harm the program running, but it was affecting the data inputs. It was like we were reading the first row twice. So that was just a short. I had to fix that short, and then it all worked. So it wasn't too bad, but there were quite a few steps to diagnosing the problem, and it would have been nice to go through that, but I didn't. Anyway, that's the keyboard tested. If you liked the video, please leave me a comment below. I guess we'll have to move back onto the VGA. So thanks for watching, and I'll see you in the next one.